Hello everyone, and welcome back to our course on using information theory to analyze complex systems. This session is the third in our series on information dynamics. That is, looking at the dynamics of information processing in complex systems. In this third session of that set, we're going to look at the concept of information transfer. So the main outcome of this session is to understand measures for information transfer and the philosophy of how this concept relates to information storage, which we looked at in our previous session. We're going to focus on the measure transfer entropy and extensions thereof, looking at them as a model for information transfer in our wider perspective of studying distributed intrinsic computation in complex systems. In particular, we're going to look at applying the JIDT toolkit using the autoanalyzer GUI and looking at extending the code it produces in order to analyze information transfer in complex systems data sets. I also want you to be able to apply the toolkit to make parameter selections for the transfer entropy and also to evaluate different choices or approaches to analysis, in particular to critically evaluate such choices. The primary references for this session are the same as for the last, including the JIDT paper, my book on information dynamics, and the Bossemeyer book on transfer entropy. So in the previous sessions in this set, we started off looking at the philosophy of information dynamics, which asks the key question of how the next state of a variable in a complex system is computed. We looked at complex systems as multivariate time series of states and concentrated on thinking about the computation of that next state as the output of a local computation within the system at that specific point in space and time. We looked at how information dynamics seeks to address questions such as where the information in that state came from, how we can measure it, how we can model the information processing in terms of how much information was stored, how much was transferred, and whether we can partition these operations or whether they overlap, and so on. We went on to look at the active information storage as our primary measure for how to model information, how information is stored in the system. That looked at measuring information storage that's in use in this computation as the mutual information between the past state of the variable and the very next time series value here. So moving on to information transfer then, building upon what we've already seen, I want you to remember what we're doing is constructing a model of the dynamics of the target variable. A model, that's a real key word for us here. We've already accounted for the past of the target in this model. We've already looked at when we're trying to reconstruct or model the dynamics here, we've already accounted for the past of the target in our measure of information storage. So we're building on that as our first step. So now we're asking how much information from the past of a source, for example, Y1 here, how much information from the past of that source helps us to predict the next state of this target, or in other words, when we're modeling the dynamics of the variable, coming back to that keyword modeling, how much information transfer would we include in the model from this source by accounting for its past influence, given that we're already considering the past of the target as our first step. That's our principal choice here, to consider the past of the target first, because that is normally how we examine complex systems. When we're looking at the state updates of a variable, we think of that in the context of its past first. And we'll look at some examples of that in the next few slides as well as later in the session. So the first example I want to walk you through uses our intuition about information transfer. This is a very simple process. We can think about these as heartbeat messages from some computer server, for example, to the phone of an IT guy, or equally we can think about the state of the IT guy's knowledge about the server. So all that's happening here is our target is simply copying the source, and the source is undergoing a very simple Poisson transitioning process. It'll be in its state of zeros or ones, whichever it is, for a long time before it switches and then stays in there for a significant time as well. We can write this down mathematically, where we've got S for our source, time step n, and n plus 1 is the updated state of the source. And we're looking at transition rates of lambda 1 for a transition to a 1 and lambda 0 for a transition to a 0. And mathematically, we have that the next state of the target is a copy of the previous states of the source. We're considering here small transition rates and lower transition rates to a 1 than a 0, so that our values are normally 0. So example values we could have here are a transition rate to a 1 of a probability of 1 in 20, and to a 0 from a 1 of 1 in 5. Okay, so I'll summarize that again. It's a very simple process where if we examine the source first, it's having long arrays of zeros or one states, which sometimes switch to the other state and then maintain that for a while before probabilistically switching back, and so on. What I want you to do here is try to predict the next few values in our series. So we're encountering some zeros. What's going to come in the next few values here? Try to think about, where would you take the information from to make that prediction? If you knew the target was just a copy of the source, sure, you could take it directly from the previous state of the source. But I want to think of an approach that we could take when we don't necessarily know that. Okay, when we're modeling computation generally, what would we do? Let's think about that in terms of modeling the destination, as we've been doing in our previous sessions here. At each step now, what I want you to do is model your own prediction of the next value, as if you were the target. Okay, as if you were the IT guy here who has some knowledge about what the previous state of the server was. Let's model your prediction of the next value that's coming. As an exercise, I want you to rate your prediction. So first of all, write a prediction down based on the past value alone. So if you know that the server's down here, what's your prediction? What's your prediction of the next value here? And how sure are you of that on a scale of 1 to 10? Okay, so what would you predict right now? If you know it's down, and you know when it's down, it generally stays down for a while, you probably predict it's still going to be down, right? But how sure are you of that? Then I want you to update your prediction based on the values that we see in the source and evaluate how much the source adds to that prediction on a scale of 1 to 10. In this case, we saw a 0 from the source. Now, obviously, when we see the value of the source, that's completely telling us the value of the target in this example. But we were pretty sure the target was going to be a 0 already, right? Because we knew it was already down, and that once it's down, it tends to stay down. And we can try that again. What would you predict the next value of the target to be now? We know it's a 0. We know it tends to stay 0 for a long time once it is 0. So again, you're probably going to predict the 0. And how sure are you of that? As an exercise, go through these steps and write down your predictions. Okay, you can stop the video and pause it and write down your predictions and how sure you are of your prediction of the next value given the past, and then click and see what the value of the source is and how much extra that adds for you. Okay, and think about when that changes. When does the source tell you more than other times? In particular, I want you to think about where the source added the most to your prediction of the target based on what you already knew from the target's past, and where it added the least and why that's the case. And we'll revisit that quantitatively in our next session, in our next short video, when we start to look at a quantitative measure of information transfer being the transfer entropy.